Hello, hello. We'll get going in just a second here. And the lights will be on in just a second too. I updated their firmware. Boop. Boop. And it's brighter today. Oh, it's a little better. Can I handle looking at that all? Oh, this says there's an... I'm such a sucker for firmware updates. Like, here I am streaming, updating my Elgato firmware. That light there has not cooperated with me, so I'm like very hopeful that the firmware there is actually going to be an improvement. So we'll get started in just a second here as people come by, and I see that I'm not privately in the right chat here. I see us going on Restream. I do not see... Okay, it does look like YouTube's going. The light restarted. Excellent connection. That's good. All right. YouTube and Twitch rocking fine. Thanks, Tyeth. I should say sorry for the air conditioning noise, but it is hot here in Seattle. It's been running for a while now, and it's like not making a huge dent, so it's going to be on the whole time, I think. Hello, Beata. I think we should get going. And I do remember, I think DCD was out, so we may not have time codes today. Or they might come late. We've got an exciting show today. I am very excited. First, let me introduce myself. My name is Scott. I go by TanNewt online, and I work for Adafruit on CircuitPython. So if you don't know those two things, Adafruit is an open source hardware and software company based out of New York City. I work remotely for them, so I'm in Seattle, which is hot, and sorry for the air conditioning noise again. So I work on the software side of things, and I work on CircuitPython, which is a version of Python designed for microcontrollers. Microcontrollers are little inexpensive computers that, hey Dishipu, that are a great way to get into electronics and programming without all of the complexity you get from like a Linux computer or a desktop computer. So those are in brief what it is. Here's an example. And we'll talk a bit more about this board. So what Adafruit does is they create these boards, and I don't know, I drew an X on this one. So this is hot off the press. This is the RP2350 Feather. This is from the first batch. And so it doesn't come, this is a PS RAM chip here. I soldered that on, and then there's this also pin here. And I'll get into why that is and why they're not in the shop yet. But that's a brief thing. Yeah, another, I have one more exciting announcement before, I don't know how many people are watching yet, but we're expecting our second kid at the end of October. I've like finally figured out like my leave plans with Phil and Lamore, who run Adafruit. So you can expect me to be kind of out completely for about 4 weeks once the baby's born. So around basically all of November, if the baby is due on the 28th. So most of November I will be out, and then I will come back while my wife is off on her work. And then once she goes back to work, I will take another 8 weeks off. And then after that, I will be kind of like, we'll see where we're at, but I may be like fewer hours than normal. So I may not be doing deep dive then as well. So that's coming. I'm excited that we can finally start talking about it. I did want to talk about it soon because we're getting to the point where like babies come early sometimes, and like I don't want it to be a surprise if I have to say like, hey, I'm gone. So that's exciting. Is my audio peaking at all? It looks like it is to OBS. Just a smidge. I'm gonna just like go down a little bit. So yeah, that's Matthias says, congratulations, thank you. Yeah, I'm very excited. It's gonna be quite the change going from a toddler to having a toddler and a baby, and going back into the newborn world. But I'm stoked. I'm stoked about it. I'm also super excited about work stuff this week. So where should we start? So it was a long weekend last weekend, and Namor had gotten the first batch of RP2350s built by a third party, and they were testing them, and they didn't all come back okay. They like half of them failed and half of them worked, which is not good, which is why they haven't been put in the shop yet. So I asked her, like, when I got back on Tuesday, like, hey, like, can I get one of these? And she was like, oh, like, they all failed, like half of them, a bunch of them failed, and I haven't had a chance to figure out why they failed. And she was sick, as folks saw on Ask an Engineer, so she wasn't, you know, super on top of things. And then the Picos came in stock. So the Pico 2s came in stock Tuesday? Wednesday. One of those 2 days. And I was like, hey, I made an order for Pico 2s. You want to throw in some of the bad feathers in there so I can help debug it? And she had asked me for advice on how to debug it. And one thing I said was like, hey, if you can get a trace of the flash, you can tell where, like, you can tell how far the bootloader's getting before it's dying. So that's what I've done on this feather that I just showed. So by putting the PSRAM down, not only do I get PSRAM, but all but the chip select line here are shared between the flash. And it has like this smaller flash chip, so it's like quite hard. So you can, I have this blue clip. I don't know if I've showed it. I've got kind of this wiring harness. So you can get these clips. Go back to here. So you can get these, they're called Pomona clips. I think I've showed these before. But they've got 8 pins here, and what you can do is you can squeeze them and put them on either PSRAM or a SPI flash chip, which is a great way to get all these wires connected reliably, or a lot more reliably than the little tiny clips. So I did that, and then what I did is I don't know if we're going to be able to see it, but this pin here, hi Garrett, this pin here, there's a little wire that's running from the flash chip select line out to this pin, so I can capture the chip select for the flash here. So that's what's on my feather, and so I got that soldered down, and I was doing debugging as to why it's not starting up, and I did that for 2 feathers, one that had passed the tests and one that hadn't. So let me go to the desktop and show you. I've got lots of exciting things this week, but RP2350 stuff is exciting, and you are seeing something else, like old conversation on Slack. Let me see. How do I guess I go this way. Let me redo it. That looks better. Turned it off and now it's on, and now you should see what I'm seeing. I don't think there was anything sensitive in there. Just the internal Slack. But RP2350 is public now, so I don't have to worry about it as much. Okay, so this is Salier. It's a logic capture thing. So all those dangling wires off that clip, they go back to this device that captures the logic signals there. So I'm not doing this live. I did this yesterday or the day before. So I'll just show you the traces that I have. So I have, down here I have good boot and bad boot. So here's timescale 0 to a second. And we can see that like there's lots of little reads and then some reads. And this is CircuitPython booting up. And then in the bad boot, we don't make anywhere near as close as progress, right? Like this first second is mostly blank. And then what we can do is we can zoom in. There's kind of two ways to look at it, from the start when the boot ROM's going, or from the end when it crashes. So what was happening, and let's just zoom all the way in. So this is the bad boot. And what we can see here is, so this is the clock line. And we can see here that it's like very, very fast and very inconsistent. So it says frequency 125 with 250. So it's like, it's going quite fast. And because the Salier is sampling at 500 megasamples a second, like this isn't giving us a consistent reading on what that number actually is. But basically what is happening is that as the chip is reading the code to execute off the flash, it's getting garbage data and crashing. That's why, so this is the garbage data that it ran, and it was garbage data because the flash was just going way too fast than what it can support. And we can see here that it's like at 16 for a little while. And then when it's, and we can see when it starts up, it's like, it's 8 or so right here, and then things get faster. So what is happening? Well, the question is why was this happening? And so one thing I've added is there's analyzers in here. So we can do a simple parallel analyzer, and this is the same settings as the other capture. So you set D0 through 3. These are your data lines, and then you have a chip select line and a clock line. I've modified the simple parallel from Salier to add the chip select stuff. So that is new, and it is published on GitHub somewhere. But it makes the second step a lot more reliable, and then you add SPI flash analyzer. So you take the input of the simple parallel with CS, and you then do higher level analysis to understand what is being done to the flash in this capture. So here you can see, for example, that it's saying like, okay, this is a quad read. So quad read means that all the data is coming back on all 4 lines, and here's the address that it's trying to read. So 041820. What you can do then is you can look at the map file, add the prefix for the flash region in the memory map, and then figure out what code was executing. It's a neat trick. You can basically trace the function. It's not perfect because once you cache the code, it won't fetch it again. But for like the first time that you access a particular function, you can kind of like know where it is at. So this is the bad scenario. And what I did is I compared it to the map file, and I found that I think it's this one. This gap here is loading the external oscillator initialization code. So this is the code that, or actually that's not true. It's not that code. It's so the other thing is there are busy wait gaps. So a 1.9 millisecond gap here, as like some startup does, and then there's another busy wait gap here. So when you're initializing the clocks, this is after the boot ROM's run. It's decided that it's going to run your code, not the bootloader. Your code needs to basically speed up everything based on the external clock so it can run faster. So what it does is it initializes the external clock, and that you have to wait for some period before that's stable. And then once and then a little bit later you switch like all of the core internals over to that faster clock. And that's what I figured out, is that this gap here is when it's doing that wait for the external oscillator to be stable, and this 500 microseconds is not fast enough. So what's happening is that the clock, the external oscillator clock is not actually stable when we're doing these reads here, which is why it's not working. So if we look at the good boot and we ignore most of this like CircuitPython running stuff, we go right at the start, and I'm gonna look for here's a 2 millisecond gap. So that's the same as not this gap, but this gap. This gap is also right around 2 milliseconds. What we can see here is the second gap where it's waiting for the external oscillator to start up is now 7 milliseconds long, not half a millisecond. So it's waiting a lot. The good boot is waiting a lot longer for the external oscillator to be stable before switching over to it. So you're missing these high. Haywire, good find, thank you. So I should also point out that this is a problem that was found on the RP2040 as well. This is not new to the 2350. The problem is that, and let me pull up the other window. Spoilers for what I want to talk about later, but I had accidentally deleted the code that propagated this the extended delay. So to fix CircuitPython, I had to add this header include back. That all of the config boards include this like 64 times multiplier to just make the delay the delay longer. It's kind of crazy. The delay is based on counting the external oscillator itself. So what's happening, it seems, is that as the oscillator starts up, it's actually generating more counts than it should, which means that the delay is shorter than it should be, because it's timing itself based on a clock that's not accurate yet. So by raising it, you're kind of just like insulating yourself from that like time period where it's counting too fast, and you're ensuring that you get to you wait long enough that even the fast counting is still doesn't speed you up so much that the clock is not stable. So we found the issue here, and then Arduino had the same problem. And I was looking at this today. Schoelhauer, Adafruit, Arduino, Pico. I'll show you this. So I just pushed to this branch, and there should be 2 commits. So I had to do the same fix where I had to add this startup delay multiplier to the RP2350 as well. So here's a condition that says if it's 2350, do these commands. If it's 2040, then it does the delay multiplier still. So it was basically that, one, I had broken CircuitPython, so nothing was doing it. So if you've had problems on RP2040s with the betas or the alphas on with CircuitPython, that's why. And then we just didn't have the same code like setting for the 2350 for CircuitPython or Arduino, so that caused a problem, and that's why the test jigs were the tests were failing. Is the code was not waiting for the external oscillator to be stable. So I've gotten a build to Lemoore, Lady Ada, and hopefully the feathers will hit the test jig, or pass the test jig and get in the shop next week. Whew. So I guess in my intro I didn't say what deep dives are. I just dove right in. But if folks have questions, I'm happy to answer them as well. This stream tends to be 2 hours. The last couple times have been different, so but this time we should be able to do the full 2 hours. So if folks have questions about any of this. Hey, Wire says, I'm curious to learn about the P4. Oh, yes, I guess I put it in the title as well. Okay, so let's keep moving on. I just wanted to, so that's good news for Adafruit 2350 stuff. We've got fixes in the works for that. Just a couple more comments before we dig into the P4 stuff. If you were using BLE on ESP from CircuitPython, I realized, we had a bug filed by Liz that BLE HID didn't work. I dug into that this week and realized that I hadn't implemented all of descriptors. So descriptor is like metadata about a characteristic on, I won't go into it, but the main thing is I forgot to propagate these flags about whether they're readable or writable, which meant that like clients didn't know what to do and it didn't work. So that's why it didn't work. BLE HID should work on the absolute newest CircuitPython now on ESP, which is exciting. That's something people like to do. I also fixed a bug in TinyUSB. So if you, I don't know if Sam's watching right now, but Sam filed an issue saying like, hey, if I put my computer to sleep and start back up again, my print output shows on the display, but it doesn't get transmitted over USB. And it turned out that TinyUSB had a bug in it. The TinyUSB had code to detect a resume from sleep, but that's just by like saying like, hey, if this interrupt is active, then we've resumed. But the problem was the interrupt wasn't actually turned on. So my fix for it was just turn on this interrupt that then gets handled as a resume, and it works just fine. And so that's in there as well. This TinyUSB update has more in it, that's why. And here's the BLE HID bug that got fixed. So that's exciting. And here's this issue. If you want to know more about the crystal stuff, this is the issue for more info on the crystal stuff. And it's from the 2040, not from the 2350, but it's the same stuff. Interesting. Okay. I breezed through the RP2350 stuff. If you have questions about it, feel free to ask me. But I've had a good hardware week. So not only did I get RP2350 stuff, I got a Bus Pirate 5 that I haven't even opened yet, but I'm excited to play around with that. And it's an RP2040, I think, so I'll get CircuitPython running on it. But I made an order for the RP2350 stuff, and then Lamore was like, oh, and by the way, it's the ESP32-P4 dev kits that she requested from Espressif came in. So it may be hard to see here, but there's two boards stacked on top of each other. This one is the Espressif dev kit. Now I knew that these were becoming more available. So the P4 was announced like a year and a half ago or more, like the start of 2023 is when they announced the P4, I think. But chips are unobtainium until you they don't exist until you actually get your hands on them. And dev kits are one of the best ways to get access to chips pretty early. So they were becoming more available. Somebody dropped by the Discord, B. Whitman dropped by the Discord, said, hey, I picked one of these off AliExpress. Turns out they actually put some of their early dev kits on AliExpress. Espressif has an official store. I didn't get that, but Lamore talked to her contact at Espressif, Lady Ada did, and got a few dev kits for us at Adafruit. So she sent me one. So I made a second order to get this thing. So here is the ESP. Oh, I guess you're seeing my screen still. Let me go back to the camera. So here's the ESP32-P4. What do they call it? The Function EV kit or something. It's the first P4 dev kit. It's the only one right now, and I'll show you in just a second on that. One thing that surprised me is that this is mounted on a big screen. Miroslav says, please switch to a full screen of your cam. Yes, I think I got it. But yeah, so this is interesting. This is the first chip that I know of from Espressif that doesn't have a radio. So the chip here is an ESP32-P4. The CPU, it has two CPUs at 400 megahertz, and they're RISC-V cores. And it's really meant to be a high-performance chip, so higher performance than S3s even. And then actually there's a C6 here on the side, so there's work in the IDF to use a coprocessor for Wi-Fi, which is interesting. But the P4 has high-speed USB, and it has MIPI, DSI, and CSI, which are high-speed differential displays and camera support, and a bunch of RAM apparently. So this display, actually, let's get into the numbers here. Let me go back to my desktop and take a look at this. So here's the web page for the P4. It's a high-performing SoC offering extensive I/O connectivity, HMI, which I think is human-machine interface, and then security features. Yeah, human-machine interfaces. So they're really like trying to lean into like driving displays and doing camera stuff. So they call out MIPI, DSI, CSI, I3C, which is supposed to be the successor to I2C, SDIO, Ethernet, and USB 2.0 OTG, but they don't specifically say, but it does have high-speed USB support, not just full speed. So for those of you following along, that's like full speed is 12 megabits per second, high speed is 480 megabits per second, if I remember my USBs right. And then low speed is like 1.5 megabits a second or something. And so you can see they have the SoC information here, and then they have this ESP32-P4 function EV board. That's what I've got. And then if we look, this is a very handy page, the dev kits page, and you can see for the P4, and look, they actually have a buy. Where does the buy link? Yeah, the buy link takes them to their AliExpress, and AliExpress doesn't work in Firefox for me. So that's where the B. Whitman person got it. Flash and PS RAM, 16 megabytes flash on board, 32 megabytes in-package PS RAM, 4 megabytes in-package flash on the C6. Interfaces, CSI, DSI, high-speed device, high-speed host, or USB high-speed host, USB high-speed device. The USB serial JTAG, that's pretty common. Yeah, and then here's the other stuff. So that's what I've got, and I was looking to see. So there's no data sheet that I have yet. If you go in their technical documents, there are links to where it would be, but they are not published yet. But the ESP IDF53 supposedly has support for the P4, and CircuitPython is up to date with that. So we're going to see how far we can get getting this going. Here's I think there's actually probably more information about the board itself. So let's just talk about this a little bit. Highlights of the P4, dual core 400 megahertz RISC-V, up to 32 megabytes PS RAM. P4 supports USB 2.0 specification, including high speed. MIPI, CSI, and DSI. So CSI is camera, DSI is display. H.264 encoder, which I saw that and I was like, that's like video encoding, and various other peripherals. Low cost, high performance, low power, network connected audio and video products. There's also a C6 module that serves as a Bluetooth and Wi-Fi bridge. Congrats. Thanks, Mark. The screen that I pointed out is 1024 by 600, which is very interesting. And it comes with a camera as well that is MIPI CSI, and it's a 2 megapixel one. So things are targeting visual doorbells, network cameras, smart home central control screens, LCD electronic price tags, two-wheeled vehicle dashboards, and then they ran out of ideas, which is what I think when you put etc. I thought it was also interesting. I just opened it today, so some interesting things I took away from it. They've gone to the like a Pi header, a Pi style header here. This is USB host, USB device, separate power, USB power, and then a USB to UART. So whenever I'm doing Espresso stuff, I'm always doing dual USB. So I have device connected, and I also have USB UART, and that I use the USB UART to do the logging out of the device to see what's happening. Here's another overview, kind of what I just said. There is speaker output port. These are 15-pin ribbons for MIPI. Micro SD card slot on the back. Lots and lots of cool stuff. So, what else do they have? Here's the bridge. Boot mode select. QSpy flash. Pinout. Hardware revision. Schematic layout dimensions. And then we're basically reading the user guide. So this person, B. Whitman, who's actually the person that does the Tulip Creative Computer, Tulip CC, which is very cool too. They're the ones that managed to snag one off AliExpress, and they dropped by. I saw them on the MicroPython channel, and they had talked about P4 support. And I had just updated the IDF to 5.3, which says that it has P4 support as well. So they did some initial legwork to get things working. So they actually got it compiling. But beyond that, I'm not sure what it does. So they did this like kind of like all of the boilerplate stuff that we need for pinouts and pin objects and stuff like that. So that's where I'm picking up. So thanks to, I think Brian is their name. Yeah, Brian Whitman, thank you for getting this started. And I'm gonna pick up where you left off. We've got an hour and a half. Let's see if we can get CircuitPython running on this thing. One thing I'm thinking about is I don't actually know the state of USB support in terms of upstream tiny USB, so that's going to be something interesting. So my first goal is I'm going to get plugged in, and I'm going to just get into my regular process with Espresso stuff. So I'm going to do dual USBs. I'm going to do the USB UART, try to get logging output there from the chip, and then I'm also going to be loading to the device port. So let's get that set up. So I'm going to plug in here to the USB UART. And it's not on because there's a separate on switch on the board. I have like 2 micro USB plugs that are always plugged in, and I have 2 USB-C ones. I have one USB-C one has a switcher as well for switching data on and off, which is very handy. So I'm going to hold the boot button. I'm going to flip the switch on. We've got a light that says 5 volts. And I should have turned on the connection. So I actually did just get it building. So it uses the ESP IDF, so I'm trying to just like fit into that mode. So usually what I have is over here I have the hi Aperture Maker, welcome. So I'm going to connect to the USB to UART thing, and I'm not going to do this one yet. This is the one that I usually have set up to be the CircuitPython serial port. And I'm actually gonna, you know what, before I even do this, I'm gonna hold the boot and I'm gonna hit reset. Okay, so we are getting data from the ROM. It's waiting for us to download to it. So now let's do, let's see if we can do a port. With like an S3, there will be another serial port that we get to the USB to UART converter. Yeah, so there's this ESP32-P4 serial connection. So that is not through the external USB to UART converter. This is actually the internal one. So what we're going to do is we're going to say flash. So we already built it, and we'll see if it works. It didn't. It didn't work. Great. So baud rate is pretty fast. It looks like, I wonder if, okay, let's see if we can lower that baud rate. I wanted one of those boards from Ali, but they were gone pretty quickly. By the way, I do not know if you did see this note from the Ali page. I think it says that it's discontinued. The current chip version is 0.1. Oh, the functionalities of USB serial JTAG are not available. Interesting. I wonder if that's actually this version. Okay, so let's ignore that. Thank you, Miroslav, for saying that. Let's try switching to the USB to UART converter instead. So we should be able to do that, but the nice thing about it's totally possible that I have that version of the chip. Okay, so now it's working. This is gonna be kind of a pain. Staying in the bootloader. So now we're gonna go reconnect. So usually, that's perfect timing. Thank you for letting me know that. Usually because I can load via the USB serial to UART, or the internal converter, I usually leave the external one just connected. But in this case, I'm not gonna do that, and I'm gonna hit reset again. And I'm just getting invalid header. Okay, so we're back in the bootloader mode. We're getting a watchdog timer. I'm not inspired by it. So usually what happens with Espressif is that they have this boot ROM that's like pretty simple, and then there's a secondary bootloader that happens after that. Invalid header. Huh. Okay. Well, that gives us something to try to fix. The other thing we could do instead of trying to get CircuitPython going is we could try to build an example from the SDK and get that going first as a reference point. Maybe I want to just try it briefly to see if I can pull it off without having to do that. We do weird things with the build system. We don't fully use CMake, so that's part of the problem. So we're not even getting to the bootloader. As far as I know from my friends from Espressif, P4 chips which are out our first batch for developers, and they're not final. So I think your board will have one of those. Okay. Would a full erase make any difference? As you say, getting an example via the IDF is probably a good step. Full erase can make a difference, but I wouldn't rule out CircuitPython build system problems. So let's just take a look at our build system here. So we don't need headers. P4 is also RISC-V. That is probably right. These registration functions are the bane of my existence, but I think we're failing even earlier than that, so I don't think that's currently the problem. One thing could be that our target architecture may be different. And this is why it might be nice to figure it out, to get an example build going. So RISC-V is weird in that it has, oh, let's close this. We already talked about that. RISC-V is weird in that it has lots of configuration options. And so that's what these are, these like ZICSR, ZIFenceI, like these are particular like sub-specs that are implemented. So I'm curious to see if this is just correct for these new higher performance RISC-V cores. So I'm just gonna go into ESP-IDF and just see if I can find where this is set. Toolchain H2, C5, C6, C61, C5, C5, C61, RISC-V. Note that these are not none of these are P4. So let's actually just take a look at the P4 toolchain and see what it says. RV32, I am a F, so F is for float, which is nice. I hate CMake. Remove no exec stack. ASN flags, CSX flags, C flags. Okay, so this is different, right? This value and this will matter. So let's take a look at this. So MABI, we're going to want to get correct. I don't think we need target, but the float support is different. So C flags plus equal that. Let's do if equal P4 else. And if, come on. Right, so the other ones do not have, it's interesting, no integrated AS would be like no integrated assembly. There was something else, some other difference, like it's using different free RTOS, I think. It's using like regular free RTOS, not that. And then let's just take a look at this file. Otherwise. Oh. C compiler is Clang here. And linker is Clang LD. So if we go back here and we look at C6 again, it's using the RISC-V 32, whereas the newer one is using a Gnosis. Yeah, so like they're switching to Clang for this as well. So we need to not do that. And this is like the this is the pain that I've signed up for with our with our system like this. So P4 target architecture is RISC-V. We don't want to set cross-compile. We actually want to set compiler, I think. No, that's a good guess. Let's look at cross-compile is a MicroPython build thing. So PyMake environment is doing cross-compile and then these things, but that's not right. We want CC equals Clang. There were two set of toolchains. Top was Clang. Oh, there's another one that's not. Oh, yeah. Okay, so that's the Clang one. Oh, I see. Okay, well, let's not use Clang then. Thanks for pointing that out. Let's make our lives simpler. If we can use the same toolchain, let's use the same toolchain. Thanks for double checking me on that. Our architecture is still different, but it is going to make it simpler. So we're going to copy that string instead, and replace it here. I do want to get us to a Clang world, but not right now. Okay, so I think that's it. Actually, let's just look at master. Hasn't changed at all. And then let's take a look at, this may need to change, but we'll get there when we get there. ROM stuff was added. Oh, tiny USB P4 flag, which if that compiles, that's very good news. But I'm looking for bootloader related stuff, like that the image wasn't, like the thing wasn't valid. Like it was a pretty big red flag. SDK config. Could be that. Partition table. Totally could be a menu config issue. Binary blobs. It's probably not the binary blob stuff. Bootloader support could be it, if there's like a different bootloader support thing. We're not doing BLE. IDF components to link. I mean, it compiled, which is great. Target offset. IDF CMake targets, bootloader bin. Partition table offset, firmware offset. Flash mode. Invalid board. Huh. I wonder where join bins is. Is that not IDF code? Oh, it's way up. Bootloader offset. Bootloader bin. Partition table offset. I suspect that that is not correct. I wonder where we find it. So this is what I would look in the data sheet. Usually, let's just see if we can find it. Offset a bootloader in Flash. Okay, so it's in the kconfig, probably. See, doc startup. Actually, let's look at the doc startup. That sounds like a great idea. Flash target image, bootloader flash. Where does that come from? Log level. Bootloader size. Custom bootloader. Okay. The other place to look is ESP IDF docs. No, that one. Here. P4. Like, look at this. You click technical reference manual into 404s. Oops. Not available yet. Where's startup here? I want the startup. ESP tool has some stuff. For like putting things together? Oh, yeah. Bootloader flash offset 2000. That sounds suspicious. Chip detect magic value. Let's just see how this changes if I switch to the S3. Yeah, okay, that's definitely a problem. You know what's cool is if you find the source, API guides, you can say first stage bootloader blah, blah, blah. They have these like conditions say like, oh, only for this chip or that chip. So when you're working kind of like across chips like I tend to do, that's a great way for you to like know the differences. But I don't see the... Oh, so it's actually figuring it out. Let's find this value. It should be in a kconfig file. Ah. There you go. Bootloader offset in flash. It's 1,000 for ESP32 and S2. It is 2,000 for P4 and C5. So I don't think we don't have C5 in here yet, do we? No. But P4 is actually 2,000. And S2 and ESP32 are correct. Okay, so let us clean. Let's stop this. And we'll do a flash. We're waiting for download, so we're gonna rebuild and see what happens. Who's excited? I'm excited. It's nice that the tiny USB stuff just seems to be in there. It's probably like some IP that tiny USB already supports. So it'd be cool if it just worked. This is the problem. I don't have, like, the build system's so bad. I don't want to go to CMake. I don't want CMake. But I did find, so if you've watched multiple of these deep dives before, I have a desire for a Python, async Python build system. I discovered that somebody has a library for Python that does analysis of CMake projects. Turns out there's like some mode in CMake you can get it to like give you a bunch of information about what would happen in whatever build system. And I was like, okay, great. Like I can write a Python, async Python library that wraps up a CMake project, which would be neat. Still wouldn't use all these targets, but. Okay, we're flashing. How big did we end up being? 800K? Fast, slow, and 3 SRAMs. Interesting. Usually that's what I like read in the datasheet. Okay, so before we hit reset, I'm gonna pull it up again, and I'm gonna hit the reset button and see what happens. Oh, we got something. Calling app main. That's pretty promising. No way that tiny USB came up. Nope. Okay, so we didn't get all the way. We started at, okay, so our bootloader is working. Great, like really great. Got to the next step. So we have our second stage bootloader. It's dirty, and that's okay. SPI's going at 80 megahertz and is in DIO mode, which is not ideal. Loading app from partition and offset 10,000. Hex PSRAM, interesting. So it's not quad, it's hex. PSRAM CSIO is dedicated. Multi-core Startup, SPI SRAM memory test, okay. We're going 360 megahertz. We've got our project info. Chip revision is 0.1, like Miroslav was saying. We've got a bunch of different heaps. 134K, 18K, 384K, 27K. Oh, and interesting that this last 7K is TCM, which might mean tightly coupled memory. RTC RAM. I generally don't want in the heap, actually. And then 32 megabytes of external PS RAM. Flash I/O is dual still, which is not ideal. But we're calling app main, and then we don't get anything else. So the question is, if we edit CircuitPython main, which is actually, you know, we have something before that. So app main lives in supervisor port. Not port init, but app main. Yeah, it's right at the bottom, and it just calls main. But let's add an ESP log. Oh, it's hallucinating again. We'll just add a Python there, and let's actually add the ESP logs to the top. Oh, it's already there. Great. So we're going to do that, and we're going to do our little dance again, which it's such a bummer that the QSPI flash is unhappy, but we can make do. It's early days still. Because we're not changing the IDF, we don't have to do anything. I'm just going to get us back in the boot ROM bootloader. Compile was quick because we just added a log. Hopefully I saved the file. Looks like I did. So let's see if something runs after this calling app main, or whether that's not working at all. So let's go. Kind of slow. All right. So we got into CircuitPython. We have our logging working. But who knows how far we're actually getting in CircuitPython land. So this is a perfect example of why I am in love with GitHub Copilot. Because GitHub Copilot is really good at writing printf statements for me. Because they're like not super critical. So yeah, let's just start adding some logging. So I'm going to go into CircuitPython's main.c. There's main right there, but I'm going to add just, I want to get more insight into how far it's getting. Basically, I want to figure out where it stops working. So I'm going to include esplog.h, and I'm going to do static main. So that was Copilot giving me that suggestion, which is really handy. So now we're in main, and let's just do an ESP log. Port init. It's probably port init. But see? Like, that was really nice. So let's do the same thing we just did. We're going to do our little dance. Thank you for that link, Tyeth. And thank you to Miroslav for pointing out the serial JTAG doesn't work. I think Lemore got bare chips too, and I wonder what version the bare chips are. But we tried it, and then we saw the thing there. So, kind of boring, but PS RAM speed is 20 megahertz. Hey, Portinit does work. So we are getting quite far, which is good. So let's add some more things. You think we're running boot.py? I would be surprised if we were getting that far. There should be a code.py to run. And let's do file system init. See how far we get. See, like, it can be... I don't know why it wants to do np init. All right, let's do that. It's pretty quick to Control key Q, Control T Q. I wonder if the upload's so quick because, well, the high speed. Topbot says, aha, using Copilot to make temp logging printfs is the best use I've heard so far. Yeah. It's also been like, when I was doing the circuit matter stuff and I was adding test cases, like there was a number of test cases that they had listed for like doing packet encoding. They listed it in the specification. I literally copied and pasted that, dumped it in the file, and then started writing it kind of like sometimes I have to like do it myself so that it gets the idea. But like, it's pretty helpful with that too. Okay, my chatting is still slower than flashing again. So we're just gonna keep on keeping on. Whatever it's doing there is quite slow. It's taking like 4 seconds. Ah, okay, so it looks like something's failing. During stack init. So ESP log I will actually buffer What does stack init do? It's possible that it's, I think if I do early, there's also an early macro that I think blocks. It works more reliably for timing stuff. Let's add even more. I don't think this will be run. And then file system init. I would not be surprised if it was a file system init problem. Not at all. So something's happening where we're dying. I think that the like printf debugging from Copilot is just like the thing that gets you in the door, and then there are some cases, and it's quite good at Python too. So we made progress. Huh. There is like a 1 second gap between porting it done and stacking it, but that could be the safe mode wait. Yeah, this wait for a safe mode reset. So, do we have an RGB pixel? Are we doing any hardware stuff? Let's just skip this and see what happens. So that's the safe mode wait. So that wait is when you can time the button press, it's that wait. It's that busy wait in there that is where it happens. Let's just see if that is causing our troubles. The other thing to always be aware of is pin resetting can really mess you up. We should at least get it quicker. So it's still not. So we didn't finish there. I wonder if, let's kind of do this same, keeping it, porting it. I'm suspicious of a lot of this. So we're not even getting to the point where we're running Python code, so we can be a little bit cavalier with not doing everything we think we should be doing. I'm surprised. You know what? Let's take a look at the menu config, because it looks like we're hanging. Component config, driver, PS RAM. megahertz. Pure RAM app. Default is 20. Is quite slow. Read help. Yeah, print registers and halt is what we want. Like, the question is, like, all right, where are we? Because if we really hung hard, we'd hit this watchdog. We want panning handler in IRAM. I wonder what that hardware PC reporting thing is. Of the assist debug module. When an exception occurs and the CPU is reset, this register will be kept. And then we can use that to debug where you were. Interesting. Yeah, we don't want Wi-Fi. Heat detection. Log output. We could bump that down a level. We'll get more output, which could be helpful. so we did a lot of changes. Oh, one thing we don't have is this never reset stuff. Which totally could be a problem if we are debug UART. Is port init? Yeah. Current task. Console UART. If debug. LF defined. What do you think? What pins do you think it is? You think it's right? No, it's not right. But the menu config will probably tell us what the defaults. Man, I can't believe that the data sheet's not available yet. Console. So I think it's slash. Does it tell me what the default UART pinout is? No. 37 and 38, that's my guess. If we hit question mark here. P4. Yeah, 43 is the default. But it looks like 37 is what we want. TX is 37. It's 37 here, but for C2 it's 20. 37, okay. Okay, somebody's leaked it. All right, I will do that. Oh, okay. I just got an email from Lamore. That looks like it could be it. Heyo! Preliminary. Pin definition. Lots of pins. This will not have changed, so we can look at here. MIPI. USB. N0, P0. N1, P1. Oh yeah, we want all the PSRAM pins in here too. Ah, here we go. UART TX is 37, UART RX is 38. So let's add that. Let's see what JTAG, even though we're not going to use it, since we're in here, let's just update all this stuff. I didn't spot it. Oh, here we go. Oh, that's right, they're MTDI. Hi, Gary. There we go. 3, 4, 5, 6, 7. Which is slightly different from this one. Since we're in here, let's just do it. It's 3 through 6. It does seem to me like maybe we're resetting flash, which we definitely do not want to do. If defined ESP. See, that's weird. This is ESP32, but we also have, I think we have a table here in Common HAL microcontroller. It does feel like we're kind of like hanging the memory bus, which is not a good thing to do. GPIO selection, pin mask reset forbidden. C2, C3, C6. We don't actually need that thing that I just added. S2, H2. Okay. So 37. 38. P4. P4. Oh, sorry, you can't see everything. Sorry, this is where I have a bigger screen than what you're seeing, and it's very handy too. So let's see. Which pins are the ones that the flash and PSRAM are using? $50 megahertz reference clock output. Oh, here we go. 28, 29, 30. $28, 29, 30. Oh, you know what? Yeah, that's right. 30, 31. Flash hold is 32, 33, 34. 2, 33, 34. And then is there, oh, here's USB D plus, D minus, 50 and 51. Minus is 50. I assume that's where where's PSRAM going? Debug PSRAM. Maybe I should start at the top. Okay, so it looks like they have 8 bits for PSRAM here. SD. Oh no, they have even more. Here's 16 DQ15 for PSRAM. Okay. Let's go to the overview. Copyright 23, so this could be kind of old. Dual core 400 with AI instruction extension and FPU. And then a 40 megahertz low power system. L2 MEM, LP, SRAM. Oh, and 8K system tightly coupled memory. 96K of L1 and L2 cache. JPEG, pixel processing accelerator, image signal pipeline, H.264 encoder, crypto accelerators, key manager, random number generator. Whoa. That's pretty wild. This is like the first glance I've had at the data sheet, so it's exciting. Security stuff I don't really care about. A lot of this hopefully we get for free. 2D DMA, that's interesting. There's a separate parallel I/O interface, but a lot of this stuff we should just take advantage of implicitly. Okay, the thing that we actually care about is the in-package PSRAM and how that's set up. Non-exhaustive list of applications. In-package PSRAM, if it has an R, and then how big it is. R16 or R32. Package is QFN 104. Interesting. Octal SPI of PSRAM supports 8-line and 16-line SPI. I wonder why we saw prints about hex. Maybe hex means 16 in their book? I guess I was thinking it was 6, but... Okay, and now we're back to the pinout where we were. External flash and SRAM. 5-stage pipeline, up to 400 megahertz. Compliant with the RISC-V debug spec. Maybe hex means it's cursed. Yeah, maybe. It also supports up to 64 megabytes of external flash and RAM. Huh. Wouldn't hex be a nibble? I don't know. We could dig into it and see. Nice. Parallel I/O controller. What does it mean? Where does it thrive? So I suspect what's happening is that I'm like disabling. I don't know if port init actually resets pins. What is it actually doing? It's creating timers, setting the URL. It's setting never reset pin, but that's not resetting pins. It's doing reset reason, then it's returning. So like, we're not doing a lot Unless unless our sleep timer is messing us up. All right, I think let's just start with that and see if we're still in the same boat. Like, let's get ourselves. I said no, I do not want to save the configuration. Let's just see. You know what? Let's do a clean and flash. It'll take a little longer, but we did set. Oh, you know what? I just undid it, didn't I? Bootloader. Interesting. There's a bootloader log level too. We're in our app now, so let's just do. This is not faster. How log level? That's not what I want. Log output. Debug. Okay. Hi, Wong. Okay, let's get in boot mode. We're gonna do a full recompile because we changed the log level of other stuff. And it doesn't compile. Unterminated if. Supervisor port. We don't need these. I don't think we need those anymore. Ah, this is our problem. JTAG we do need. I didn't actually need the clean there, but it's okay. Okay, so we are trying to figure out why CircuitPython stops working. Could be a timer thing. We're not doing any flash stuff yet. We made progress. We got into the bootloader and out to our code, so that's really good. When we started today, it wasn't even getting into the second stage bootloader. And it's early days, given that these are early chips. I'm very interested in this, though. High-speed USB is mighty quick. Any ideas folks have that they could do with a chip like this that they couldn't do before? It is definitely kind of similar to like a IMX RT class. Although it's dual core, 400 megahertz. Oh, I guess the higher end RTs are still single core, if I remember right. All right. Let's try again. Oh, okay, so we did get further. We got all the way to run code.py. We did, look at that. Why do you think it's that way? We got more logging. So what was 20 megahertz? The PSRAM connection was 20 megahertz, I think. Okay, so let's go back to main and see. It works with this stuff. Comment it out. Works. I don't think Circuit Pi boot counter. Okay, so let's just do port heap init. I don't think actually does anything. Serial early init. I don't think that's too. What things should I get from Adafruit? What do you want to do? That's the question. What do you want to do? Okay, let's just do a quick another test. Just to see. I know most of the microcontroller side of things. Not so good at the other stuff. Man, the flashing is going like pretty quick. Small scale project with IR and BLE plus Wi-Fi. If you want to do BLE and Wi-Fi, I recommend the ESP32-S3. That's an easy one. So take a look at the S3. It's got Wi-Fi and BLE, and it should be able to do IR as well. IR is not used that much, so if you find bugs, join the Discord, which is the middle chat, or the chat above me. You can go to adafru.it/discord to check that out. Okay, so it still worked. Mike says, got a Pico 2 yesterday. What is your opinion on the 2.2 volt latching errata? Is high impedance broken on the regular GPIO pins? It's been getting a lot of attention from some people, and I'm sure, like, I don't know, it happens. There's a lot of other cool features about it that are still really cool. I fully expected them to come out with a new revision anyway. Given that they had like said that they were trying to find bugs and stuff. Like, so I mean, it's unfortunate they found it after launch, but like I am very much in the camp of you can't know everything beforehand. Toddbot says BLE on the S3 is good to go now. Probably. It's a lot better. It's getting there. So yeah, try it for sure. Try BLE on the S3 for sure. I just fixed descriptor stuff that was causing BLE HID not to work. Okay, let's do this and try it again. This is like my life doing ESP IDF stuff, so welcome. Welcome to my world on how I do ESP IDF stuff. I am a printf debugger through and through. It's pretty quick if you're not doing all the other stuff. Okay, so it's still got that far. Which is interesting given that I feel like tiny USB should be coming up. Like the only thing I'm not doing is the safe mode wait. Is that right? printf carrying the game. My defense for printf debugging is that it works in almost every situation. Like, regardless of language where you are, like getting print output is something that you usually can do. I was shocked when I got into embedded and I had to actually debug by LED blink, which was kind of outrageous, but like, yeah, I was surprised by that. Okay, so let's just try the safe mode wait again and just see if that's what breaks us. Although our USB is not coming up. So there's that. And this is what happens if you forget to go like that. This has probably been stated before, but what are you trying to do now? So I got a new chip, the ESP32-P4. It's a high performance chip from Espressif. It does not have Wi-Fi natively on the chip itself, but it runs at, this is being clocked at 360 megahertz, so I'm trying to get CircuitPython running on it. We'll see. We'll see what it says. We're in the bootloader. I don't know if there are any LEDs on here. Okay, so now it works. Oh, you know what? We did fix the reset thing, didn't we? Maybe it was the pin stuff that was causing the problem. Nothing like finding a missing comma. Yep, that'll do it. Oops. What, I was like, wait, is that CircuitPy drive ours? But no, it's not. So I think run code.py may actually be working. But our USB is not coming up, it looks like. So what I want to do is I want to, in global serial, I'm just going to print out, because I think if code.py runs, it should print hello world. So let's do, let's just print it out. Early init, connected, read, bytes available, write substring, tag, text. And for whether we're connected, we'll just say yes, we are. Let's see if we can get a hello world out of this to show that the VM's running, which I suspect it is. I thought that's the way I did it. I think I've done this before. Also do, which is a little weird, but does that work? Ha, it does. I don't know why, but it does. Okay. We're loaded. We're waiting. Heyo! There's our hello world. our UUID, board ID. Okay, so Code.py is running, but TinyUSB is not working. Does TinyUSB have P4 support? I don't even know. I wonder what pins it's connected to. It is plugged in. Step one, make sure it's plugged in. Okay, so the thing I'm gonna do now is I'm gonna go, there is a way to debug. I think there's a way to turn on TinyUSB debugging. Or I can just manually do it. Let's take a look. USB support would be nice. TinyUSB. Source. Portable. Espressif SX. But my guess is that and you know, this could be the problem. This could totally be the problem, that we're including the wrong TinyUSB source. Yeah, let's pull it up. We're trying to treat the USB as the S series USB. Okay. That doesn't work at all. So this is what I was worried about. Does our copy have it? Did Ryan update it and I didn't realize it? No. So the other thing is that Espressif has a fork of TinyUSB. And let's look at the branches. Or are they not using TinyUSB at all? N.4. That's not helpful. Pull requests. Huh. Okay, so it is Synopsys DWC2. Into release 15. Okay, here we go. Here we want, this is what we want. Source common. Source common TMCU. Sorry, I'm gonna edit this file to do this. Line 305. It's not 305 anymore. So I'm adding that. So it's the same IP. It's got 15 endpoints, which is going to be awesome. And then in source portable synopsis DWC2, we add opt MCU ESP32-P4. And then in that header file, peripheral count 2. I wonder if we could do host and USB at the same time. That would be amazing. Okay, so I'm gonna keep, I know I'm off screen for what I'm editing, but I'm literally just like doing these changes. And we need to upstream them. Like, what the heck? Upstream these. Okay, so synopsis, DWC2, ESP32. Peripheral diffs and USB peripherals is replaced by sock interrupts.h. And then this stuff is all new. So copy this, paste it here. EP Max. They get rid of EP Max. But then they also have this stuff. All right, maybe I should cherry pick it. I can have Taka, who does Tiny USB, he can figure this out. Copy. One is a full-speed peripheral, and one is a high-speed peripheral. Interesting. Yeah, maybe I should just cherry pick this. This would explain why it doesn't work. Int enable. I haven't even gotten. Oh, I guess I'm through most of the change files. I wonder if they don't have high-speed mode working. Boards. I should probably be showing you the opposite. What I'm adding. Okay. Source. TUSB option. Expressive. H3. No. Good guess though. Okay. And this is annoying because our numbers here will be different. And we don't use their CMake. try again. We're in download mode. We should also see if they changed any of these files. But if it came up, that would be awesome. I was looking at their branches. Default active branches, but then they also have all branches. Release v15. Let's see what the UVC, so that's webcam stuff. Fix error for endpoint close. We probably want that. Refactor names of endpoint counter logic. So there is some stuff that we probably want. Change hierarchy names for P4. Yeah, so we just got this stuff from here. All right, I gotta wrap it up. I gotta use the potty. I gotta go pee. So let's wrap it up, and I'm gonna keep working on this. If you wanna follow along, you can, I always push to my own copy of CircuitPython. So if you do github.com/tannewt/CircuitPython, I'll push this up to back it up before I'm done. Thank you all for hanging out for these 2 hours for Deep Dive. It's been a pleasure. I'm going to keep poking at this, see if I can get USB going. I might just try to rebase all their changes on it. I don't know. I don't know exactly how I'm going to do it. I wish they would upstream, which would be great because we do other cool things in upstream, and we want to use that. If you want to support me, you can go to Adafruit.com, purchase some hardware there. Hopefully we'll have Feather RP2350s in the shop next week sometime, if all the testing goes to plan. And keep an eye out. P4 stuff we'll start hearing more about, but I don't know when it'll hit the shop at all. So thank you all. I'll see you next week, and on the Discords, ada.fru.it/discord.